So today is an investigation into injectivity, surjectivity, and then their categorical generalizations. So monomorphisms, epimorphisms, and then we're going to be looking at how these relate to the concept of isomorphisms. And then I'll try to tie this all together into equivalence of categories if I have time at the end, which I believe I will. Okay, so let's recall the following simple fact from the category of sets. So a function f from A to B, where A and B are sets, is an isomorphism if and only if f is injective and surjective. So the first question is this just a tautology, right? Because maybe you think that the definition of an isomorphism of sets is a function which is injective and surjective. Well, that's not true, and it might seem like splitting hairs at this point in time, but by the end of the lecture, it is absolutely not going to seem like splitting hairs. What we're taking as an isomorphism is if there exists another function g from B to A such that the two possible compositions give you the identity. So f of g is the identity on B. And g of f is the identity on A. So in particular, this is not a tautology. Okay? So that's the first thing to realize, is that this is not some vacuous statement. There's indeed content here. Okay. And we will recall that a similar statement holds in the category of complex vector spaces. So if f from V
sorry
to W...
to interrupt, but there's someone's halo is in the orb cam, so if you're a bit close to the orb, maybe take a step back. Yeah, Martin, maybe you want to retreat. Yeah, that's great.
Cool. Okay, so I've formulated this sentence badly. Okay, f via the W, a linear transformation between complex vector spaces V and W is an isomorphism if and only if it is injective and surjective. Okay, so we've seen two categories now where you get this concept of injectivity and surjectivity being sufficient in order to prove that indeed you have an isomorphism. And there are more categories where this is true. If you take the category of groups, you've got a similar statement. But the point is that this is not always true, right? So the canonical example is the category of topological spaces. I think that this is pushing the prerequisites a little bit too far in order to um, write that down as an example and to prove it. But we can say the sentence that you could have a continuous function which is both injective and surjective, but that does not mean that the continuous function is a isomorphism. We'll look at a more down-to-earth example later on in this lecture, but what I want to emphasize is that we're going to be refining our understanding of this concept, and the concept in our hands is that of an isomorphism. We're going to be refining our understanding of that by generalizing and looking at a greater level of abstraction. We're going to be looking at general isomorphisms inside an arbitrary category. And then when we do that, we're going to realize that there are some categories where we get a theorem like this, and then there are some categories where we don't. Now, I think that this is very interesting because we've kind of zoomed in by zooming out, right? If we just worked inside the category of sets, then we would fall into the lazy mindset of thinking about the first statement as a tautology. It just doesn't really matter. You can think of an isomorphism either as a function that admits an inverse or a function which is injective and surjective. It doesn't matter because we have this equivalence between the two concepts, right? Um, However, once we generalize the concept of isomorphism and injectivity and surjectivity, and we look at a broader range of examples, suddenly we refine our understanding of isomorphisms even in the category set. So we're going to kind of zoom in by zooming out. And I really liked one of the pieces of art that was generated by Dal E2 that I posted in the Discord server um, pertaining to this lecture. So what one of them kind of looked like was a big monolith. So you have a big pillar here, and then you have another one, and then the rest of them come in pairs, but they come in pairs of different levels of kind of conjointness. So you have these two that are very close to each other, and then you have another one where it just wasn't exactly identical to each other. So you get kind of something like this, and then it looked like they were getting further apart sometimes, and then sometimes they were close together again, and then this kind of went off into infinity. So this motivated the title of this lecture, The Gap Between Equivalent Concepts. So we can think about this pillar as the category of set, and we can think about this as two pillars. One of them is the concept of an isomorphism, and one of them is functions which are injective and surjective. And you can see that it's the same pillar because it's the same thing. So how could there possibly be a gap between these two pillars when they're the one pillar? Well, one way that there can be a gap between them is when you generalize the concept and look at broader examples, and you realize that in some other category, you do, in fact, get distinction between the two concepts. So maybe that's the category of topological spaces, and this is generalization. Okay, so first I want to generalize the notions of injectivity and surjectivity. And as I already kind of alluded to, these give you the concepts of monomorphisms and epimorphisms. So, definition. Okay, so this is a definition where the defining property is an implication, right? So we have a morphism, F, from A to B inside some category C, and that morphism is a monomorphism if it satisfies the following property. If for all morphisms GH that map from some object inside C to A, that satisfy the property that F composed with G is equal to F composed with H, we have that G is equal to H. Okay. Now, if this looks mysterious, it shouldn't, because don't forget, I can squeeze this in here, that injectivity says f of x equals f of y implies that x is equal to y, right? And so monomorphicity is replacing x and y with morphisms, g and h, which is all that an arbitrary category can do, because we don't know that the objects inside an arbitrary category are entities that contain elements inside them. That's only true of certain categories. So we have to generalize out to morphisms. I mean, it's the correct notion anyway, but it's a very similar definition to injectivity. Okay, so this one is kind of easy to remember. All right, let me move over to the next set of boards. Okay, and the first lemma is in the category of sets. A function f between sets A and B, or from set A to set B, is a monomorphism if and only if f is injective. Okay. So the proof is, first we assume f is a monomorphism. And we're going to prove that it's injective. So let x, y be elements of A, such that f of x is equal to f of y. Then what we do is we introduce these two new functions. So we define g to go from the set containing a single element to A, where bullet gets sent to X, and then we do something similar for H, but this is going to map to Y instead. Okay, and then what we notice is that f of g of bullet is equal to f of g of bullet, which is equal to f of x, which by hypothesis is equal to f of y, which is equal to f of h of bullet. Okay, and so this implies that f of g is equal to f of h. And so since we have a monomorphism, since f is a monomorphism, we thus have equality between g and h. So that's an equality of functions. And so when we evaluate at every point, we get the same output. And so this implies g of bullet, which is equal to x, is equal to y is equal to h of bullet. Okay, so that proves that if you have a monomorphism, then the function is injective. Now we need to do the converse. So maybe let me write on the other hand. On the other hand, let f be injective. Okay, and then what we need to do is say if it's the case that I have two functions in my hand, g and h, such that f of g is equal to f of h, then I need, like under that assumption, I need to prove that g is equal to h. So say we have two such functions. Okay, then we can perform a calculation for x an element of C. We have f of g of x equals f of h of x, which implies f of g of x equals f of h of x. I don't need that bracket. And then you can see that the fact that g of x is equal to h of x follows immediately by injectivity, right? So f is injective, and we literally have f of something that is equal to f of something. So those two somethings are equal to each other. And that holds true for an arbitrary x, so that is sufficient to prove equality of functions.
I had a question about this, actually.
Yep.
Thinking about the converse direction, I was wondering if you could like generalize it to talk about like these functions from the terminal object, just the set with the bullet in it, to the set A. In that, like the category of set sort of has this property that that like all of the functions from the terminal object into a set A kind of characterize that set uniquely. So this is sort of a vague question, but I'm wondering if there's like a way to like generalize this so that like that concept of injectivity sort of is equivalent to being a monomorphism.
Yeah, that's a good question. So the category set has exponentials, so I think that you can get...
Yeah, the relevant
something
concept
like
here
that.
is a generator. So an object is a generator of a category if morphisms out of it detect distinctions between morphisms. So an object C is a generator if for any pair of morphisms fg from x to y, if f is not equal to g, there exists a morphism from C to x such that f after that morphism is different to g after that morphism. So that's so the 1-point set is a generator of the category of sets. You'd also get there with exponentials, as you said, but that's a much stronger hypothesis. Many categories say of interest in geometry have generators, but they don't have exponentials.
Okay.
All right,
Cool.
so could you define a concept of kind of injectivity but for generators and then show that, I don't know, in some circumstances that's equivalent to being a monomorphism?
Well, it'd just be HOMs out of, well, so if your category has a generator, then you can treat morphisms out of that object as essentially being elements. And in particular, monomorphism will be the same as what you expect with respect to those kinds of pseudo elements.
Yeah, so
Uh-huh.
if you have a generator, you'd be able to only check monomorphicity on morphisms out of that generator. Is that the point?
Right, so suppose you have a morphism which satisfies the kind of injectivity condition with respect to morphisms out of the generator.
Yeah, exactly. So
So
we have this. So if this implies G is equal to H, then F is a monomorphism.
right, so to prove that, suppose F after, I don't know, T and S were equal. And then suppose for a contradiction that S were not equal to T. Then you could find a morphism from G to the common domain of S and T and precompose with that, and you'd reach a contradiction.
Yeah, you contradict the definition of a generator, presumably. Okay. So the previous lemma shows us in what sense monomorphicity is a generalization of injectivity. And then we want to generalize surjectivity as well. So here's the next definition. A morphism F from A to B in the category C is an epimorphism if for all pairs of morphisms G and H, but now these morphisms have domain B and codomain C. And the composition is the other way around. So G of F composed with H of F. If these two things are equal, then G is equal to H. Okay, and in the category of set, we get this lemma that a function is an epimorphism if and only if it is surjective. So where do I go now? I go over here, right? Yeah.
Chad's ahead of the game.
Okay, and we can look at the proof of this as well. So first I'll prove that if F is a epimorphism, then it is surjective, and I'll do this by proving the contrapositive. So I'm going to prove that if F is not surjective, then it is not epimorphic. Okay, then there exists some element inside B which is not an element of the image of F. And now, using this, I can construct two functions g and h, where I can compose these with f in order to get the same function, but g and h themselves are not going to be identical. So this is a bit of a sleight of hand. So I'm just going to map B into the 2-point set. So bullet star, and it maps everything into bullet, right? And can you see what I'm going to do for H? I'm also going to map into bullet star, but now what I do is everything goes into bullet except for this special element B, which is going to go into star, right? Now, since B is not an element of the image of F, once I pre-compose these with F, we're not going to see a difference between those two functions because we're never going to map into star because we don't have that element B in the image. However, these two functions themselves are not equal to each other. So this is going to map into star if y is equal to b, and it's going to map into bullet otherwise. Okay? And then I'll just remark that g of f equals h of f, but g is not equal to h. Okay? So f is not an epimorphism. Okay, and now I need to prove the other direction. So now what I do is I assume f is surjective. And assume that I have two functions, g and h, such that pre-composing with f gives me equal functions. Okay, so I just need to prove that g and h are equal to each other, which means I need to prove that they evaluate to the same thing under all of, they map the same input to the same output, right? But I can do that via f because f is surjective. So I can check every element inside B just via f because I have a surjective mapping. So let y be an element of B. There exists x in A such that f of x is equal to y. Thus, g of f of x is equal to h of f of x, which implies g of f of x equals h of f of x, which implies that g of y is equal to h of y. And since y was arbitrary, that shows us that g is equal to h. Okay, and that's a proof. So now I'm going to talk about isomorphisms, but maybe I'll just pause for questions if there are any. Let me check the chat as well. Okay, let's move on to the next board. Definition.
case it's of interest. So your argument there essentially shows that the 2-point set is a co-generator of sets.
Cool. Yeah, that makes sense. I'm just pausing because would you expect the co-generator to be the initial object inside the opposite category, right? I mean, you've got the terminal object inside set is a generator, and so you can prove monomorphicity using that generator. But if I look at the if I look at the opposite category of sets, then the co-generator is not an initial object.
Mm-hmm. Yeah, it's while it's true that one shouldn't conflate these things. Being initial or terminal and being a generator or co-generator are not that closely related a priori.
Yeah. Yeah, okay, that makes sense.
Actually, co-generators are usually highly structured, very non-trivial objects in many categories of interest.
Okay, dimorphism F from A to B in the category C is an isomorphism if there exists a morphism G from B to A such that F composed with G is equal to the identity on B and G composed with F is equal to the identity on A. Okay, so this is almost verbatim what I wrote down earlier inside the category of sets. Literally, the only difference is I'm considering a morphism here instead of a function, right? But we can see now that with this general definition, we can then go into particular categories and work out whether we have this theorem from earlier relating injectivity and surjectivity to isomorphism. So this part of the lecture comes with a big warning. In general, even the generalizations of injectivity and surjectivity are insufficient in order to give you that the function's an isomorphism. So monomorphism plus epimorphism does not equal isomorphism. Okay, and that's not a bad thing. That's just an observation about these concepts. So you can find categories and you can find morphisms inside those categories, which are both monomorphisms and epimorphisms, but those morphisms are not isomorphisms. Okay, and we're going to look at an example of that. So the key point is that inside some familiar categories, you have a concept of surjectivity, right? So in the category of sets, in the category of groups, in the category of topological spaces, in the category of complex vector spaces, you have surjective functions, right? And those things might not necessarily be epimorphisms. So the core example that we're going to be looking at is in fact the inclusion map of the integers into the rational numbers. So that just sends an integer to the rational number n divided by 1. Okay? Now, there are a few things to note. One, this is clearly injective. Two, this is clearly not surjective, right? 1 over 2 has got no element in the domain that maps onto it. 3, I have not told you what category we're looking at this in, right? Because this could be a few different things. So Z could just be the set Z, and same with Q. But if I think of both of these sets along with the operation of addition, then they're both groups, right? And if I look at both of these sets along with the operations addition and multiplication, then they're both rings as well. So what I have written here is vague, right? And what we're going to see is that we get different phenomena when I look in different categories. So inside the category of rings, this is both an epimorphism and a this is a epimorphism, but it's not surjective, right? And in the category of groups, we're going to see that this is neither an epimorphism nor a surjective map. Okay? So whether this thing is an epimorphism depends on the structure that I consider this map with, right? So looking in the category of sets, or category of rings, or category of groups gives you something different. So I want to explore that now. By the way, we have these shortened names for epimorphism and monomorphism. So epic means epimorphism. And monic is a monomorphism. So this is not epic and not surjective, but in the category of rings, this is epic and not surjective. Okay, so first let's look in the category of rings. So I won't give a full definition here, but if you haven't seen a ring before, then just recall that a vector space is a set along with an addition and a scalar multiplication. So if we're looking at complex vector spaces, we have some vector space which is our set, and I can add two elements of that set together. But I can also multiply by something inside the set of scalars, which in that instance is the complex numbers. Rings are different to that, where you ask for the scalars to be the same as the underlying set of the scalars to be the same as the underlying set of the vector space, right? So examples are the category of integers, because I can add integers together, but I can also multiply integers together, and the ring of rational numbers as well for the same reason. I can add I can add rational numbers together, and I can multiply rational numbers together. And a really important property of rings is that they have multiplicative identities, right? So rings have additive identities, just like groups, i.e. i.e. 0, right? So in the ring of integers, 0 is the neutral element for addition, so n plus 0 is equal to 0 for all n. But they also have multiplicative identities. So think about the number 1 there. So in the ring of integers, 1 multiplied by n is equal to n for all n. And ring homomorphisms have to preserve both of these identities, and in particular, they have to preserve the multiplicative identity. So one, well, let me say it like this. So these are such that f of 1 in R is equal to 1 inside S, okay? And this tends to be the root of a lot of the counterexamples that you find inside the category of rings. Okay, so what we're going to do is we're going to say G and H map from the rational numbers into some ring R, okay? And say we have that F composed with, sorry, other way around, G composed with F is equal to H composed with F. I just wrote F again. Okay, and we're going to prove that G is equal to H. So what we do is we let X be an arbitrary element of Q, right? And I'm going to show that G of X is equal to H of X. Now, since X is a rational number, we know that this can be written as the ratio of two numbers, like rational number, ratioinal numbers. We can write it as a ratio. So let PQ be an element of Z such that X is equal to P divided by Q. Okay, and what we're going to do is calculate G of X, which is equal to G of P divided by Q, right? Which is equal to G of P over 1 multiplied by 1 divided by Q. Okay, probably not much controversy there. Let me clear up some of this mess. Okay, and now this is kind of the crucial step. So G of P this is equal to G of P divided by 1 multiplied by G of Q divided by 1 to the power of negative 1. Okay, that's the inverse element of Q divided by 1. So that is easy to show. All you notice is that G of 1 over Q multiplied by G of Q over 1 is equal to G of Q over Q, which is equal to G of 1, which equals 1, right? And so therefore, this thing is the inverse of this. So G to the power of negative 1 is G of that element.
Maybe it's worth mentioning that you did two steps there, in that you used the fact that G was a homomorphism and then you exchanged G of 1 over Q for G of Q over 1 inverse.
Yep. Yeah, so Billy's talking about this step. two steps there. First, I use that G is a homomorphism, and so therefore preserves multiplication, and then I pull out the inverse. Okay, and now G of P over 1 and G of Q over 1, these are both elements in the image of F, right? Sorry, not F, iota. So that weird I on the left is iota. That's the inclusion map from the integers into Q. So that is equal to G of iota of P multiplied by G of iota of Q. So what I can do is the same thing. I can do the same calculation now for H, and I'll see that I get H of iota of P times H of iota of Q, right? And so therefore, if I get the two compositions, I can pull out the iota and show that G is equal to H. So I want to write that down, but I'm right at the end of my boards. That's a shame. Okay, follow me. Okay, so so if G of iota is equal to H of iota, implies that G is equal to H.
Well, there was
Then
a question, by the way. Someone asked what iota was. Maybe just you could
let's
clarify
write
what
that
it is.
here. So iota is the inclusion from the integers into the rational numbers, and it just maps an element of n to n divided by 1.
Okay, thanks.
Yeah, no worries. Okay, then our calculation shows that G is equal to H, right? Because what I've shown is that these two composites are equal to each other. So what we have is that the functions G, or the homomorphisms G and H, are completely determined by their behavior on the integers, right? So this, in fact, is an epimorphism.
Hey, I don't think you meant what you wrote at the top. I think you mean to write H of X is equal to the product of those two things.
Yes. So yeah, you're right. I need my lasso tool. Okay, so let me.
Wait, and also, are we? What are we proving? Are we showing that iota is an epimorphism or a monomorphism? What is it?
We're showing that it's an epimorphism. So yeah, I just didn't write the conclusion right. So H of X equals H of iota of P times H of iota of Q, right? And if iota is such, sorry, if G and H are such that G of iota equals H of iota, then that implies that.
But wait, isn't that what we're trying to show? We're trying to show that it's an epimorphism.
Yeah. So, oh yeah, I've written the wrong thing here as well. So you're right. Okay, so just get rid of that implication. So I'm trying to show that it's an epimorphism, right? So assume that G of iota equals H of iota, right? Then what I've shown is that H of X equals H of iota of P times H of iota of Q, since g of iota equals h of iota, we have that this is equal to g of iota of p times g of iota of q, which is equal to g of x. So I've shown that h of x is equal to g of x under the assumption that g of iota equals h of iota. That tells you that iota is an epimorphism.
Uh-huh. And saying g of iota equals h of iota, like another way of saying that would be that g and h agree on the integers
Yes.
sitting inside q.
Yeah. Yeah, that's exactly what it says, right? Okay, so that's kind of cool. That's kind of interesting. We can see that the inclusion map is clearly not a surjective function, but it is an epimorphism. Okay, and then it's very easy to show that this is also a monomorphism. So iota is an example of a monomorphism, which is also an epimorphism, but is not an isomorphism.
And we're using that isomorphisms are in surjective in the category of rings.
So we're not necessarily using that. It's more that an isomorph, just use the categorical, I mean, you can, but just use the categorical definition of isomorphism. Then you don't need to work out what the, you don't need to use this fact that injective and surjective gives you isomorphism, although you can. But the point is, this just
yeah.
clearly doesn't, huh?
Okay,
Sorry.
I just meant I was trying to follow your argument that we've shown that we have a monomorphism, which is also an epimorphism, but isn't like we clearly showed that it's not surjective, but then you concluded that it's not an isomorphism.
Yeah.
So I was just curious what the path to not an isomorphism was.
Well, I'm just saying that this clearly doesn't admit an inverse. So there isn't even there are no homomorphisms from Q to Z because
Uh-huh.
you need inverses to map to somewhere, and they just don't, right? Because there are no. So think about it like so. Let amount of letters J. So let that be a homomorphism of rings. Then J of 1 equals J of 10 divided by 10, for example, equals J of 10 multiplied by J of 10 inverse, right? And so, therefore, J of 10,
What do you mean by J of 10 inverse?
the inverse element of J of 10. Like, this would have to be true if J exists, right? But clearly, what this means is that J of 10 is mapping to an element which admits an inverse, but that's inside the integers, right? So J of 10 is therefore equal to plus or minus 1, and that's going to be true of all the elements inside Q. So therefore, this is the map that sends everything to plus or minus 1. And so in particular, J of 0 is equal to plus or minus 1, and that's a contradiction. So that's just not a homomorphism.
Yeah, I think well the logic there is a little bit confusing. So I think what you want to say probably is that J of 1/10 times J of 10 is j of 10 divided by 10 is j of 1, which must be 1. Therefore, j of 10, that is 10, must have an inverse in z.
Mm-hmm.
The way you wrote it kind of presumed it had an inverse already or something. Like the contradiction was kind of latent in the notation in a way that maybe was a bit unclear. I think that maybe was what confused Billy briefly.
Yeah, sure. It's still legitimate though, right? I mean, you can say assume J exists, then J of 10 has an inverse, and that's a contradiction eventually.
Mm-hmm. Yeah, just didn't strictly follow from the calculation you wrote down.
Okay. All right, so let's conclude. It is easy to see that iota is a monomorphism and an epimorphism, but is not an isomorphism. Okay, and that's the conclusion that I wanted to get to. So something else that we can do, although it's a little bit involved. I'm not sure what to do. Maybe I'll set this as an exercise and we can discuss, because it does lie outside the prerequisites. I want to make the statement. So let's write fact. Iota from Z into Q is not an epimorphism in the category of groups, and the sketch of a proof is to consider mapping Q into Q mod Z. And so it's this modular group that I don't want to get into. But the argument is that I can define two different maps from Q to Q mod Z that agree on Z. One of them would just be the canonical projection, right? So you just send Q to its equivalence class. And then another one would be to multiply by 2 or something before I do that. So send Q to 2 times its Q's equivalence class. And you can see that these are not the same map, right? Because 1 over 10 gets mapped to the equivalence class of 1 over 10 in one case, and then to 1 over 5 in another case, and these are distinct equivalence classes. However, they agree on Z because everything just maps to 0. All of the integers just map to the same equivalence class, and the equivalence class represented by 0. So that's an example of where you can compose two maps and get equality even though they're not equal to each other, and so therefore this iota is not an epimorphism. And that's kind of interesting because you can see that we've got this context dependence here. So when we thought of iota as when we enforced the structure of a homomorphism of rings, then we got an epimorphism. And when we merely enforced the structure of groups, then we got that it was not an epimorphism. Okay. So now I want to talk briefly about equivalences of categories. So we've looked at isomorphisms of morphisms inside categories. So what would be a correct notion of equivalence between categories themselves? Well, one observation that you can make is that a functor is itself a morphism inside a category. So the category of categories exists, and you can just look at the same definition of an isomorphism inside that category, right? So an isomorphism inside the category of categories is just a functor F that admits an inverse. But the problem is that that's just not how we want to think about equivalence of categories. It's insisting that we work on the level of equality of objects, which is a bizarre notion. That's kind of what Billy was talking about last time. So I'm speaking loosely here. I'll write something tangible in a second. But the point is, let's go back to that image that I drew on the second board of this entire lecture. It was that image that was created by the AI, right? We saw that there is like some notions of isomorphism and injectivity and surjectivity where they line up perfectly, and sometimes there's kind of a gap between those two concepts. Well, inside the category of categories, the gap is kind of so large that what sits inside that gap is a different notion of equivalence, which is a weaker notion. And we use that for equivalences of categories. And this is most compelling when you just go ahead and look at an example. So what I'm going to do is I'm going to write down the definition of an equivalence of categories. And then I'm going to write down an example, which is going to make it look a lot more transparent. And then I'm going to summarize with a collection of warnings / observations that we've made by moving to general theory, because there are a few trapdoors inside this lecture. Okay, so definition. A functor f from C to D. So these are two categories. Wait a minute, have we defined functors in this class, Billy?
Yeah.
Oh, we
Yeah,
did?
last time.
Okay,
That's
okay,
what I
good.
did the last one.
All right, thank God. Okay, thanks. A functor f from C to D is full if the induced map on morphisms
I reckon Billy's squirming at the word induced a little.
Is he?
Am I?
It's not induced, it's part of the data of a functor. There's no inducing that has to happen.
So let me think.
So you were projecting and you're squirming.
Well, you should have been squirming. Shame on you.
Okay, so we can just get rid of the word induced if you want.
Yes, please.
Okay. Okay, no more squirming. So it's full if the map on morphisms is always surjective. So this just maps an element of that set F to FF, right? Which, yeah, Dan's right. That is part of the data of a functor. So we just ask for that to be surjective. And it is the functor F.
Trivially induced.
Yeah. Well, I guess we don't need to get into it, but did you define a functor as a collection of functions on the Hom set, or did you say something like for every morphism f from x to y?
I said consists of, and then I wrote 2 bullet points. The first being a map on objects, and the second being a map f, x, y parameterized by objects x and y.
Yes, that's a collection of functions. But maybe you didn't say the word function. Anyway, it doesn't matter. And it's faithful if this is injective. This is always injective. Okay, and then lastly, F is... Oh, I haven't been underlining. So these are the two definitions I've defined, full and faithful. And then F is essentially surjective if for all y, which are objects in D, for all objects y and D, there exists an object x in C such that f of x is isomorphic to y, right? And so you can see why we call this essentially surjective. It's not surjective on the nose. There might be objects inside D that are not mapped onto by F, but we always get at least an object that is isomorphic to the element Y, right? Okay, and that's in the spirit of category theory. I believe that Billy last week was making the point that we want to look at objects up to isomorphism because what we're really using are the morphisms inside the category. And so if we've got preservation of structure, then what greater identification could you ask for from the internal perspective of categories? And so this is a reasonable definition to make. And these and this is a sufficient condition to ensure that F is part of the data of a equivalence of categories, which I haven't defined yet. So maybe let's
It's
define
funny.
that.
'Cause I think it'd be fair to say that like there's probably I think there's like 10 different questions of like why isn't this any other way? Like some of it seems kind of like for example, would you say it's is it also like essentially injective or something? Because there's no mention about like you can't there's no preventing like two objects in C mapping to the same object in D, right? Is that allowed for an equivalence of categories?
Yeah, that is allowed. So because
So like
think
I
about
guess
a
the
category
question
is
is like,
equivalent to
oh no, he disappeared.
So
There was
his,
a
his
there was
drone
a
has
small
left.
man hiding in him the whole time.
That's pretty funny, though.
Who is this? Who is this imposter?
Oh, that's pretty funny.
Okay, so the example that I'm going to end up giving, which I can just look at now, is you go from
Wait, are you still answering my question, or have you
yeah,
moved on?
I am. So you go from C matrices into complex vector spaces. I suppose that has to be finite, yeah. So the category of finite complex vector spaces. And CMAT has objects, natural numbers. So think of that as the dimension of your vector space. And a morphism from N to M is an M by N matrix of complex numbers, right? And so this is going to be the familiar equivalence between linear transformations and matrix representations once I've fixed a basis, right? So n is mapping to C to the n, and then a matrix. Yeah, gets mapped to So this is Cm to Cn, Z maps to N, MZ. Okay? And
This
then
is a
this,
good example to me of the category of complex matrices. This is a good example to me of like showing that categories are about the morphisms and not the objects, because like the objects are just natural numbers. Like there's like on the right, there's like when you talk about complex vector spaces, you're like thinking about like how much structure those like spaces have within them or something in the objects. But because this is going to turn out to be an equivalence of categories, it sort of shows that you can shift your perspective almost entirely onto the morphisms, and just the objects are just things that you can connect the morphisms together with.
yeah. Yeah, for sure. But you do also care about the dimension of vector spaces, don't forget. So like,
Yeah,
yeah.
yeah, as it almost.
Yeah, yeah. Okay. And so to answer your question, Billy, uh, if you were to think about an inverse map to this, right, it would have to be sending all of the different vector spaces of dimension n to the same element n, right?
Mm.
So you don't have injectivity of that thing, but that thing has to be faithful and full and essentially surjective because it's part of the data of equivalence of categories.
Mm.
So yeah, you don't ask for this to not. So you don't ask for injectivity on the objects. I mean, you can see that this example where we do want an equivalence of categories, we don't even have that, right?
Also, it seems to, I guess this is another question. It seems to me that um, that if f is not essentially surjective, like is the response to that always like, okay, let me just like throw out all the extra junk in the category D so that I get an equivalence of categories by
Huh.
getting rid of the stuff that isn't isomorphic to some f of x.
Nah, 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 nah. So you have an embedding in that case, and that's really important. So an example of what those extra elements might be, they might be constructed via universal properties on the embedding, the embedded elements, where D might be a category that has that structure, but C doesn't, right? So the canonical example there is the Oneida embedding. So if you take a category C, and you embed that into the category of functors from C op into set, then this is full and faithful, and that's what Oneida's lemma says. So this is an embedding, but it's not an equivalence of categories because there's tons of stuff inside here that's not inside C. But those examples are limits and co-limits and exponentials and all this stuff. So set to the C op, I guess I should say that C has to be small, but whatever. Set to the C op is a topos, right? So you've got tons of structure inside that category that you don't necessarily have inside C. So sometimes what you want to do is embed your category into something that does admit that categorical structure. And so those extra elements are really important. You don't want to throw them away.
I think we need to like pay a fine every time we mention some concept that hasn't been defined yet in the course, because we've both done that about 10 times so far, and I'm feeling bad for the audience. I think you guys should be rioting at this point.
I think we've only done it
um,
when we're answering questions, although that's probably also not strictly true. Um,
mm,
yeah, I mean, I could just say no. If you say like, is the canonical response to throw away the extra stuff? No, right? And that's a prerequisite friendly answer to that
yeah.
question. And I can say
Well,
let.
I guess maybe a weakening of that question is like, is the category where you throw, like, can you in in most situations, can you like sensibly like think about the smaller category, or like I don't know, is it ever interesting in its own right, like other than being the embedding of the category you started with?
um,
Well, I actually let me maybe answer my own question. It's like, say if we had started with with complex vector spaces in general, we might be motivated to like we've got an embedding here, and then we go, oh wait, let me just. That's kind of what you've done. You've gone. Let me just take the finite ones,
mhm,
because you have an embedding into like uh, the category of complex vector spaces, but now you're throwing out the infinite dimensional ones so that you just have
mhm,
the finite ones.
mhm. Yeah, that's true. So, yeah, that's a specific example, right? Again, I can answer this question using stuff that we haven't covered. Um, so I'm going to go ahead and do that, and I'll pay my fine. Uh, you also might not have an equivalence, but you might have an adjunction, right? So you could be in, you could take complex vector spaces, and then you can take there's a functor from set into this where I take the free complex vector space generated by that set, right? Now that's not an equivalence of categories, but there is an adjunction. So the free one is left adjoint to the forgetful functor, right? And so
Oh.
there is so you can have like a weaker embedding. It depends on how you want to think about adjunctions. But yeah, there is a zoology of ways that categories can sit inside other categories. Sometimes they're an embedding and these get studied. Sometimes they're an equivalence and these get studied. Sometimes they're an isomorphism of categories, right? So you do have a notion of isomorphism inside the category of categories, and those things do come up. So sometimes that exists. And then an example of a weaker quote unquote equivalence would be to have an adjunction between some category and another. So then you can also have adjunctions followed by embeddings, right? So you might have like some smaller category that sits weakly inside another one via an adjunction or something.
Mm-hmm.
So I think that all of the different combinations that you can think of are relevant in contrived examples, right? So I think it's not so helpful to think about like, oh yeah, cool. The canonical thing to do is to look at the embedding and look at the extra categorical structure, or the canonical thing to do is to pass to the skeletal category, or the canonical thing to do is to throw away the extra elements. It's just there's a whole array of things that can happen, and we have a theory that allows us to talk about them. Okay.
Uh-huh.
We're
Yeah,
getting
that's
bug
a
eyes
good
from
point.
category theory. Did you see the comment in the chat?
Yeah. Very
Okay,
much
so
so.
I need to conclude. Let me move over to the other boards. Okay, so let me just draw up this summary. And I'm only going to talk about things within the bounds of what we're talking about and what we've spoken about to this point inside this summary. So we had the generalization of injectivity into monomorphisms, and we had the generalization of surjectivity into epimorphisms or epics. Okay, and then we noticed that monic plus epic does not equal isomorphism in general, but it does sometimes. Okay, and then the last thing to note is that what we looked at was the definition of a full, faithful, essentially surjective functor. And an example of an equivalence of categories. But I haven't written down the definition of equivalence of categories yet. So I owe you a definition of equivalence of categories. But I can tell you that such a thing is a pair of functors, fg, with f from C to D and g from D to C, satisfying some conditions, right? And so the important part here is that an equivalence of categories is a pair of functors, right? So the statement is going to end up being, if f is a functor which is full and faithful and also essentially surjective, then it is part of the data of an equivalence of categories, and we'll get there. And also, in order to write down the definition of an equivalence of categories, we need naturality. And this is the topic of next time. Okay. Okay, that's it for the lecture. So I'll open up to questions now.
Thanks, Will.
Awesome, thanks.
No worries.